coming. So today we have a Pascal Gollin from Primorska, who was former member of the discrete group, and we talk about dominated balance separators.
Yes.
In these liners.
Thank you so much for the invitation to come back here and present my recent work. So yeah, as you said, I'll talk about result on dominated balance separators in wheel-induced-minor-free graphs, which is recent joint work with Maria Szynovsky, Matthias Kearns, and Martin Milanic. Maria from Princeton and Matthias and Martin from University of Primorska as well. All right. You all probably have heard of Robertson and Seymour's grid minor theorem, but just in case, let me remind you. So Robertson and Seymour proved that. So let me formulate it in the following way. Excluding a planar graph as a minor yields graphs of bounded tree width. So I don't necessarily want to make some of these statements here too precise, so I hope you get the idea. So this is the celebrated grid minor theorem. You may wonder, if you have not seen it before, why would we call that the grid minor theorem when the word grid does not appear anywhere? But it's really hidden in the word planar graph, because grids are the universal graphs for planar graphs. So excluding some grid as a minor yields a graph of bounded tree width would be an equivalent way of saying this. All right. So, but some of the machinery that appeared around this is regarding a concept of balanced separators. And while you may have heard the statement of this theorem before, by the way, I don't want to go into the precise definition of tree width. If you have never seen it before, imagine the graph has somewhat of a structure that kind of makes it look like a tree. And this has very nice algorithmic properties and structural properties. And this is one of the main ingredients of the whole theory of graph minor structure theory. One of the fundamental steps in the beginning of that theory. All right, but let me move on to the concept of a balanced separator. And here I may be a bit more precise for a second. So we call a set S of vertices of a graph a balanced separator if no components of G minus S, so if I delete S from the vertex, no component has more than half of the vertices. And this is kind of a very useful building block in this whole theory. So somewhat having low tree width means quite quickly that we can find balanced separators, like finding somewhat a central edge of the tree, deleting the vertices in the separator, separates roughly into half only. So yeah, deleting a back from somewhat the middle can make sure that we have such a balanced separator. But on the other hand, the size of balanced separators is somewhat tied to this notion of tree width. This is also what Robertson and Seymour proved. So so many of the basic ideas were there, and then maybe from like Dvorak and Noreen, it's from a result of theirs, it's also a bit more hands-on. So from their results, we can also say that if small balanced separators exists in every subgraph of our graph, then the tree width is bounded. So that's kind of the reverse. So the grid minor theorem reformulated So we can use balanced separators to say excluding a planar graph yields a balanced separator of small size. Slightly weaker statement formulated like this maybe, but using all the theory behind, not really weaker. Okay, so this is a bit of background on graph minor theory. So now I want to talk a bit about an induced version, possibly of this theory. So instead of graph minors, we want to look at induced minors. So induced. So we say graph H is an induced minor of a graph G if H is isomorphic to a graph that we can obtain by contracting edges or deleting vertices. So in contrast to the usual graph minor operation, we are not allowed to just delete edges. So we can contract edges and delete vertices. And we get rid of loops, parallel edges, and so on. So we shouldn't worry too much about loops and parallel edges for this talk. And in recent years, induced minors really have gained some traction. So a lot of graph structure theory has been tried to extend to this realm of induced minors. Some things work well, other things are suddenly much harder, and one of the ways to look of what could an equivalent statement in this new setting, or an analogous statement, I should say, for the grid minor theorem in this induced setting could be is an analog of this version using balanced separators. And that is a conjecture that was first at least written down by Gartland and Lokshtanov. And that conjecture says, and now let me be a bit more precise. So for every planar graph H, there exists an integer k, so k can depend on h, such that every graph G that excludes h as an induced minor has a balanced separator, and now we cannot say of bounded size, because that, as we discussed before, would mean the tree width is bounded, and we definitely know that could not be true, since if our graph G would be a very large clique, clearly the only induced minors it contains is disjoint union of cliques. So none, no planar graph other than K4 and K5 could work, and we know that, of course, complete graphs have arbitrarily large tree width. So the notion instead of small size, the measure that we want to use for these balanced separators in this setting is that these balanced separators have small domination number. Which is dominated by at most k vertices. And maybe you can easily see how this really can kind of destroy this example of cliques. Of course, if you just pick one vertex of a big clique, that vertex dominates the rest. So if we take then the neighborhoods of that vertex, the whole clique is being vanished in that now possibly balanced separator. So this is really a decent notion inspired by the recent area of coarse graph theory, how we can address this problem. And yeah, so we don't really have a well-behaved analogous notion on tree width yet on such a setting. So in particular, you could, of course, ask, oh, maybe this is, if you have thought about these things before, related to maybe a width parameter where we take a tree decomposition, and instead of the size of each bag in the tree decomposition, we ask to bound the domination number of this tree. But this is not necessarily a well-behaved notion, and it's not yet known whether a similar thing, like I said for the Dvorak-Noreen thing, about if every subgraph has balanced separator of that size, of that type, we can bound the width of such a tree decomposition, is still also an open question. But these balanced separators do still have some useful algorithmic consequences. So, as I told you for tree width, of course, and you may know there are all these types of meta theorems that many problems we can solve in polynomial time if we can formulate them in a certain type of logic. But balanced separators for some problems are still enough to give us some computational benefits. So for example, problems like the maximum weight independent set, but also many other problems in graphs where we do have these balanced separators which are dominated by few number vertices have a quasi-polynomial time approximation scheme to solve approximately. So that's somewhat of the CSE motivation for these types of problems. Where, of course, from the maybe pure structural side of point of view, it's also kind of interesting how this plays out.
So for those vertices dominating a balance separator, these vertices could come from outside of the separator.
We don't really care that much, yes, because we may as well put them into the separator and the statement doesn't change. So, but yeah, in effect, what I will construct later, they will just always be in there because it's often convenient to do so.
So this quasi-polynomial time approximation operator exists if for every subgraph you have this separator or a 3D composition where each peg is bounded.
That should be true if I think it is true if we take into account a weighted version of balanced separators, about which I will talk about actually in a minute, because that's what we are actually also proving. That so if for a balanced separator we take so if we have a weight function on the vertices, and instead of saying each component has at most half of the vertices, we say each component has at most half of the weight. Then if we have these weighted balanced separators which are dominated by a small number of vertices, which is, I think, slightly stronger than just saying for every subgraph we have it, but it implies that we have it for every subgraph, then we have the cubitas. Yeah.
Can you remind me? So you said cubitas approximation. For independent set, for example, you don't get any approximation, right? For example, for independent set on, let's say, PT free graphs.
Yeah, I think in general not on PT free graphs. Yes.
I'm just wondering where does the approximation?
Or wait. So this is not quite part of our work. This was done before. So all of this has been observed by Maria, Stefan Tomasé, and the Filipchuks. Right. Right. So. Okay, I don't think I can answer this to you on the fly. I would need to look back into the work of them to say more on this. Okay, but yeah. So what is known about this conjecture? Let's start there. Actually, very early on, by a result of Jafash, we have balanced separators if we exclude a path. Some more results were known, and I'm trying to find them in my notes so that I can be complete. Here they are. So it was also known for excluding a cycle. I think also by some result of Maria and others. By a result of Ojong, Tony, Jungho, who's not here, and myself, we can also say it's true for when H is the disjoint union of triangles. That's a Erdős-Pozsár type statement in this coarse setting. It's true if we exclude a subdivided claw, a K5 minus an edge, and the 4 wheel. And that's everything that we found until we wrote that paper where this is true. And for some of these things, we proved now a common generalization. So our theorem now is the following: for every integer L, at least 3, there exists an integer k such that every WL, so the L wheel, that is the cycle of length L together with the vertex dominating that cycle. If we exclude that as an induced minor, then we have a balanced separator of size, dominated by at most k vertices. So generalizes some of the previously known results, so that but yeah, it's still just of course a small step, but it seemed like a next logical step. Because let me quickly, without writing down too much, go to the maybe somewhat related settings. So this is just one way to try to lift a grid type theorem into this setting of induced minors, which is with these dominated balance separators somewhat inspired by coarse graph theory. Another useful setting has been the setting of tree independence number, or alpha tree width, where this comes up. So there we look at tree decompositions where instead of the size of a bag, we measure the independence number of a bag, and there's a grid theorem-like conjecture from Ojong, Martin, Sebastian, Matias, Andrea Munaro, probably I forget Claire, Hilaire, maybe I'm forgetting some people, you can correct me.
Kenny Fruger? Kenny?
Kenny, yes, Kenny, thank you, I forgot Kenny. And they conjectured that excluding a planar graph as an induced minor and forbidding a star as an induced subgraph should be enough to bound the tree independence number. And there's a result of Martin, Mujin, Sebastian, and Claire who did prove that result for wheels, which maybe was done about a year before this result, and that in our results kind of implies their results. So it's a slightly stronger variant of this. And maybe a third setting, maybe a bit more general. So in graphs of bounded maximum degree, Chuka-Kohonen and I think it was also Gartland and Lokshtanov proved, so the three of them, or was, no, this one was Tuka alone, I think, the great theorem for graphs of bounded maximum degree, yes. So if we exclude some planar graph as an induced minor, and our graph itself has bounded maximum degree, then it has even bounded tree width. That's what Tuka proved. All right. So much I wanted to go into the history. So for the remaining half hour, I want to sketch some of the proof ideas. So now would be a good time for questions before I start going into the proof.
How bad is the function k as a function of L?
Very nice, actually. So so the precise numbers that we are proving are so for every graph. So if we exclude WL, either we are dominated, the balanced separator is dominated by L vertices, or the dominated separator even has only size L minus 1 squared.
Oh, so you can take
So-
k to be L by L squared.
So we can definitely take k to be L squared, but slightly stronger, we can either say it's L or the separator even has a bounded size. So it's slightly stronger than just saying L squared.
So for the partial ones, like if you remove some of the edges between the center and cycle, you can do this.
I mean, we exclude it as an induced minor, right? So we exclude all. Yeah. Well, no, okay, no, not quite. Sorry. Yes. I think okay. If we would subdivide something on the cycle, I think our proof would still work. We haven't formulated it in that way, but I'm pretty sure our proof would fail if we would try to subdivide spokes. So it's really important for our proof that this was a vertex with L neighbors on the cycle. Yes. Okay, more questions? So then let's move on to the left side here for now and talk a bit about the proof ideas. So one useful concept that didn't come from us, but came from Gartland, who did kind of the first thing when I said this was true for paths, and that is the concept of Gartland's paths. At least it's Gartland paths. I hope I write his name correctly.
Yeah, another accent on A, both A's.
Oh, on both A's, okay. Thank you. The main idea for this is that in any graph we can find a balanced separator which is just the closed neighborhood of a path. And the idea is as follows. So I don't. I only sketch proofs. I don't make precise proofs. But basically, if we already have constructed some path, and the closed neighborhood of that path is not yet a balanced separator, well, then there will be one component. There will always be a unique component if something is not a balanced separator that has too many vertices, right? So there can never be two. So let's look at this unique component. And what we now kind of want to do is we want to kind of grow this path into that component to make this component then slightly smaller and so on. So basically we would like that that this vertex here has maybe a unique. Sorry. This should be an induced path. That's an important property. So this vertex here will have, of course, will hopefully have a neighbor here in the neighborhood of this path, which then has a neighbor here. We would like to grow it like this. But maybe this would then no longer be an induced path because maybe all of its neighbors towards that component is already seen. So, but that's not too big of a problem. Basically, we can choose like minimal subpath here that already covers the whole neighborhood towards this big component. And then the last vertex of that subpath, because of the minimality choice, will have a private neighbor towards here. That's if we now take this path instead, we would, and its neighborhood, we kind of shrink what the big component is, the unique big component. And that's the rough idea how we can always find an induced path as a balanced separator. So let me write this down. So for every graph G, there is an induced path P such that the closed neighborhood of that path is a balanced separator. I should say everything that we are doing for these kinds of weighted separators that I explained before to Unjong's question. I'm not necessarily writing this down, but later in the proof it will be a key aspect. But I don't always want to write there's a weight function on the graph and a weighted separator, since I only want to give you the rough idea of how the proof goes. Okay, so these are Gyarfas paths, and what we first do is we kind of extend this idea to what we calling Gyarfas cycles. Well, we're calling them Gyarfas cycles not because Gyarfas invented them, but just it's an analogous idea, just using cycles instead. So now, if we are starting with a Gyarfas path, and let's take a Gyarfas path of minimum length. So basically, then if we are stopping one vertex before the last vertex, so let's say this is here a vertex P1 and this is here vertex PL.
So when you say Gyarfas has a minimum length, you mean the one that has balanced separator, or?
Yeah. So a Gyarfas path is one with a balanced separator. But I also don't care about minimum length. I just want that this subpath is not this subpath and its closed neighborhood is not a balanced separator. That's the minimality property that I want. Okay, but yeah. So this red path and the neighborhood is not a balanced separator. But if I add the purple vertex, then I am a balanced separator. So now if I only delete the red path and its closed neighborhoods, again I will have one big component. And well, that big component will happen to contain that vertex. Not too important, but okay, no, the component will not, because it's in the neighborhood, sorry, but it will look something like this. And again, we kind of use the same trick here. Let's pick a minimal subpath that covers the whole neighborhood towards that heavy component. So, and we can do, and why we do this, we make sure that this guy has a private neighbor towards this component, and this guy has a private neighbor towards this component, so that this still is all induced. And then in this component plus these two vertices, we can just choose a shortest path between them to obtain an induced cycle. And now having this induced cycle and deleting its neighborhood, its closed neighborhood, it's not quite necessarily a balanced separator, but just deleting that one more vertex and this neighborhood then will be a balanced separator. So because this heavy component, just adding this vertex and its closed neighborhood would have broken up that component, even if we're just looking at this path, and this vertex would have broken up that component by the choice of this path, because it covered the whole neighborhood here. So so now what we are finding is this object here. So for every graph G, technically I skipped one case, namely the case where this here is just one vertex. So in that case, we find a balanced separator of size 2. So either, or dominated by 2 vertices, there is a balanced separator dominated by 2 vertices, or there is an induced cycle C and vertex V such that the closed neighborhood of the cycle union V, so the closed neighborhood of everything, is a balanced separator. Okay. So I didn't really sketch the full proof, but this is really the idea. There's not much magic happening here. So, any questions up to this point?
Sorry, why did you write the process statement? So there is by the separator and 2 vertices.
This was just because I possibly have slightly lied to you. Because if this red path is just one vertex, then we don't find the cycle. So, but then those 2 vertices and their neighborhoods are enough. So, and I didn't at least want to lie with the statement. I didn't gloss over some proof details, but.
So far we didn't use any wheel-induced-minor-free.
Correct. So this is true for every graph. That's why I wrote for every graph. And I think the proof that showed that it worked for cycles was also roughly along those lines. But yeah. That I don't think this is an explicit proof that was written. That was implicit in some other work. So from Maria and others, when they proved something else. Okay. So now, so here we had the cycle and then extra vertex. Let's forget that extra vertex for now. Let's just look at the graph where we delete that extra vertex from our graph. We know that we have it in the background if we need to. So now the main idea is, let's say we have our cycle here, and I'll draw the other vertex in there as well. And we know that if we have take the neighborhoods around here, then we are a balanced separator. Okay, so we know that. So let's look at now just the cycle. So for, don't care about this vertex for now, but let's look at just this cycle and the graph obtained after deleting that cycles. This graph will have some components left over.
You're not deleting the neighbors of the cycle?
not the neighbors anymore, just the cycle. Right, and at this point we don't really ask yet if is this alone even already a balanced separator, because the cycle may still be too large, right? But now you will neatly see where the wheel comes in. So every component, so if a component has at least L neighbors onto that cycle, then we can contract that component and find a wheel minor. So forbidding a wheel minor really controls that every component only sends few edges to that cycle. So now we go to that point. Let's assume one of these components is heavy, or has more than half of the vertices. Let's say this one here. So let's say this one is big. But then, if one of them is big, then let's look at those vertices here, which are L-1 at most, and this vertex here, that was the one we had in the beginning. And what we can actually show, it's pretty straightforward, that just taking those vertices and their closed neighborhood only shrinks this component. So this will actually be now a balanced separator, dominated by these L vertices. There's slight technicalities there that so that we make sure, but all these other components basically remain small, and this component compared to the component where we deleted the whole neighborhood of the cycle and neighborhood of this only gets split up possibly into multiple components. It cannot gobble up something of the other weight. That's the basic idea. Okay, so no component is big. Every component is small. And now comes the big step. What we now do is we contract every component to a single vertex. And here is where it comes in that we are working with weighted balanced separators, because every new of these contracted vertices we are modifying by giving the whole weight of the previous component as the new weight of that vertex. So what we are ending up with is a graph that is just a cycle plus an independent set of vertices. Each of those has at most L neighbors on the cycle, or strictly less than L neighbors, at most L-1 neighbors on the cycle. And the next big thing is just analyze this graph, because our goal now is, so these graphs looking like this, we're calling cobwebs. So our next goal is to just analyze what happens if we do have a cobweb, now with this given weight function, so that every vertex has weights less than a half of the total weight. And we want to find a balanced separator and now of size at most L-1 squared, which is just contained on the cycle. Because if we can do that, if we don't cheat by picking one of these internal vertices, but just ones from the cycle, then once we decontract, we can translate that balanced separator of small size again to a balanced separator of this whole graph. Right, and so the proof until here is quite short, and the proof that this works is really the main work in this paper. And let's try to spend the last couple of minutes to sketch some ideas. So this will be even more sketchy than the proof so far. I hope the proof so far is kind of really giving you the overview of the brick strategy. And now I will have to skip a lot of details. Okay, questions so far? Okay, so let's first see kind of where this L-1 squared kind of comes from. So let's say we have our cycle, and let's focus now on a single vertex here, which has its L-1, at most L-1 neighbors on this cycle. So if I look at one of these segments here, which is bounded by like two consecutive neighbors in this order, in this cyclic ordering along the cycle, then I can kind of ask how well is in the whole graph, where we have now also all these other vertices, is this segment here connected to the rest of the graph? And and actually, one thing we can think, so if the rest of the graph here, which is all these other vertices plus the rest of the cycle, so let's look at this component of the rest of the graph. And if this component has more than, or at least L neighbors onto this segment, then again we can contract that component and find a wheel. So actually, we find here a set of at most L-1 vertices that kind of separate the component of this segment from this big component. So one thing that can still exist, let me use a third color, is like some vertices glued to here, which are only attached to that segment and nothing outside. So so that thing is still here, but everything else that contains this rest of the cycle only has few neighbors here. So so assuming now that deleting these at most L-1 vertices are not a balanced separator, we will find out that either this component here is big, or this component here itself, what was left over here, so the yellow stuff attaching to the green stuff is big. And this is something that we can do for all these like wedges here simultaneously. So we ask this wedge, we ask this wedge, we ask this wedge, and so on. Something like this. We can take all these from all these. So we have at most L-1 wedges, and for each of them we have the set of size L-1. Is all of this together a balanced separator? If the answer is yes, we are happy, we found the balanced separator that we're looking for. If the answer is no, then actually one of these wedges, together with everything that just attaches to that wedge, that will be our big component. So more precisely, for every vertex here, we select specifically one of those wedges which is heavy. And now the idea is if we kind of want to pick specific vertices that minimize this length of these segments, or not necessarily the exact length, but no strictly smaller segment here is also big. And these are, let's say, the good selections that we are making. So if this is such a good selection of one of these wedges, and let's say we select for a different vertex another good wedge, then this will kind of look like this. So good wedges may overlap like this. We will never have that good wedges will be disjoint, because then we would have a heavy component somewhere here in the graph and a heavy component somewhere there in the graph, and that's a contradiction. Heavy components always need to intersect. So, and because of the structure of this graph, they have to intersect on this cycle in this wedge-like way. So, so just doing this right minimality choice here can guarantee us now that that if we what did I want to say? Yeah, if we take now these sets from these two things together, then we kind of separate not just each one here from the rest, but and there's a lot of detail that I'm skipping now, that we can separate even this intersection here from the rest of the graph. So specifically for every pair we can now select, so for every pair of these good wedges, so that minimized or for which the segment here was minimal, we can find that the intersection here will also can also be separated by now at most 2 times L minus 2 vertices from the rest. And in my last minute, so technically we have to go one step further and don't look at this for 2, but look at this for 3 together. So if we would have one wedge like this, one wedge like this, and one wedge like this, so looking at 3 together, now, as I said before, they all need to intersect. So we have here this intersecment between green and yellow, here between purple and green, here between yellow and purple. But if we delete all of those 3 together, we can really separate everything. And this is the detail that I'm skipping here. But basically, just making this maximality choice is enough to guarantee that for these 3, those in that case, the L-1 vertices from that, the L-1 from so the L-1 from green, the L-1 from purple, and the L-1 from yellow are enough to separate everything. But that proof alone is about a page long, so I cannot hope to sketch you much more in the remaining
But
minutes.
that's not L squared.
No, the L squared came from here. So this is 3 times L minus 3 in this case. But to make our choice of which is the heavy segment, we had to, so in order that we can make that choice, we had L minus 1 squared. So we had L minus 1 possible wedges, and so if every wedge would say, oh, not this wedge is heavy, but the remainder is heavy. So that's a situation you kind of need to rule out. So everything says, oh, the rest is heavy. So that we have to rule out, but that we can rule out by making sure we're taking all of these, and then all of these components are really separated. So there is no remainder component. So every component is one of these. All right, other questions?
Okay, let's thank the speaker.